Okay, so here we are. We've got a few lectures before the next exam. Read for sure these first 3 sections, and then, so where were we? We're here today, so we're behind, but we're going, and we did this kind of out of order. We ended up doing like density of states earlier. We're probably going to drop off conducting polymers and then do tight binding approximation today, which is then going to leave us with 2 days for carbon. So we're still going to do carbon. We're going to drop out this. So be sure to read chapter 9 in the big book. Okay? So that's kind of what you're looking at going into the midterm next week. So there's a homework out now, which I think we said due Friday. I'll put another one out on Friday, which we'll have due on Tuesday at 1. I'm having trouble finding a room here. I want to move my office hour to before the exam because I think it's regularly on Thursday. So I want to move it to Tuesday. I just can't find a conference room. So it's, but hold on for an email about that. Okay, and then the exam will be Wednesday. Similar to last time, I'll probably shorten it by a few questions. Okay, any questions on that? No? Yeah?
Will the midterm cover homework 6?
Yes, absolutely. Yep.
Will the answers come in
Yep. Yep, it'll come out, like, I'll have it as soon as you turn it in. So you'll have, like, all afternoon.
It's about homework. Will we get penalized for only turning in the graded questions?
Only in that, if you're not prepared for the midterm, I mean, yeah, I mean, this is a tool that you can use to study for the test. But yeah, no, I'm not, I don't think we have the, yeah, right, Rosie? The answer is no. Yeah, you will not be penalized.
So you're not checking for completion on those, you're just only looking at the ones that was graded?
Sure, yeah, let's do it that way. It's, yeah, so we'll call it optional. Yeah, those are optional. Okay. But they're totally fair game for the midterm. Yeah. So if you want an A, you need to understand them forward and backwards and the variations that could come from them. Okay. Other questions? Okay. So last time we kind of rushed through this. So we had talked, let's see, we talked kind of extensively about a metal and when a metal, when can you shrink a metal small enough that it's no longer a conductor and becomes an insulator? And we kind of looked at a couple ways to do that. One was just thinking about the de Broglie wavelength, which was kind of unsatisfying. And then we also looked at a valence model and considered the valence electrons, and I think it was 4 times the Fermi energy over 3 times the number of valence electrons. And whenever that became greater than KT, no, less than KT, then we could consider that to be an insulator.
Maybe it was greater.
Oh, that's
Right, so when it's less than, it's an insulator, right? Yes?
Why would having a metal be an insulator be useful?
I mean, what if you wanted to build an integrated circuit and you wanted to be able to control whether that tiny area is an insulator and conductor? So you could switch in and out this and turn it on and off to be an insulator and conductor by putting on another valence electron. That seems pretty useful. So what we kind of rushed through then was how do you define this for a semiconductor? And so we talked about when you promoted an electron and created a hole that we could kind of consider this thing to be like its own hydrogen atom. And we said that it was an exciton. We called this thing an exciton, right? So you can kind of think of it as a particle with a nucleus and a rotating electron. And that this has a size analogous to the Bohr radius, right? Just like the Bohr radius has a size of 0.53 angstroms, this exciton also has a size. And that we said we could calculate this exciton radius based on the Bohr radius, this exciton mass, which we described as kind of a combination between the hole mass and the electron mass. Yeah.
When you say combination, you mean simple linear sum?
I don't think it works that way. I don't exactly understand how it comes up. These are all tabular values, but yeah, I don't think you just average them. You would be given that, yeah, yeah. And then the permittivity of free space and the permittivity of your material of interest. And again, these were all, I'm not going to dive into this a ton, but you can definitely calculate this, and these do exist for a variety of different semiconductors. And so this was a table that we had for example, these different semiconductors, including some of the most popular quantum dot materials, these like, for example, cadmium sulfide, lead sulfide. And so here is all of these different materials, so including the Bohr exciton radius. So this is the size that you can get. This is the answer, right? So you can go up to 18 nanometers with lead sulfide and still have a quantum confined system, right? So that's pretty big, right? So the exciton is essentially 18 nanometers, yeah.
So that's an exciton with a nucleus and one atom?
Mm-hmm. No, don't think of it as an atom. Think of it as a hole delocalized in your semiconductor.
And it sort of orbits that delocalized hole. The hole can move.
Yeah, totally. Yep. So if you have your valence band and your conduction band, and you have, I think this draws it better than I did. I will. Right? So if these are all of the atoms in your semiconductor, and they're and so the electrons are all delocalized over this, so there's essentially one big wave function for this entire material. This particle can essentially be, this exciton particle can travel in that, across that semiconductor. Yeah. Because that is in many ways a mechanism of conductivity, right? Yeah. Was there?
Talk more about excitons. I'm a little confused about how exciton works, and how it's able to exist.
Do you believe that a hole exists, and so that you could have?
It's also it's so big. How could it have a radius of 18?
How could it be that much bigger than? Yeah.
A single electron hole system for one exciton, right? But it's spread over an area where there are going to be hundreds and hundreds of electrons.
Other electrons.
Yeah.
Exactly, and hundreds of other protons, right? So then it kind of stands to reason why you could have these sizes that are bigger than a Bohr exciton, right? If we look at this table, this is 11, 3, 18, which are all much, much bigger than 0.53. And this is even nanometers. So that's 180 angstroms versus 0.53 angstroms for hydrogen lead sulfide. So it's like 360-fold times bigger. And it's largely because of this. If you only have one electron and one proton in a system, it kind of makes sense that they're going to be attracted to each other a lot strongly than if you have all this other delocalized charge that can satisfy some of the attraction between these two. Right? Okay. And we talked about this. Yes. One other useful relationship then is this equation. It's not often that people still get equations named for themselves. Like most of the good equations have all been claimed. But this person is still alive and got an equation named that a lot of people use. And so what this does, the Brus equation, is it relates the energy of that exciton or the energy of emission of your quantum dot. This is specific for quantum dots. And it allows you to calculate that based on the radius of the particle, okay? So as the radius of the particle increases, you're going to have less and less energy in the system, right? Where this is just the band gap of your semiconductor, okay? And there's a homework question that uses this, and in that, you want to use a slightly modified version that is H. So you can just write this as the exciton mass. I think that's what that question in the homework gives you. Okay, as opposed to how they have it written here, where it's both the mass of the electron and the hole.
Is that H to the R power?
It's this exact thing. H to the, yeah, you're right. That does look like an R, doesn't it? I mean, because it is an R. It's 2. H squared. R does not equal 2. Okay, so that's kind of fun. And so then if you can plot this, so this is just the expression as a function of radius. Okay, so when we have bigger quantum dot particles, we're more red shifted, smaller particles are more blue shifted. Okay, yeah?
I'm going to jump back to the algebra on the last equation. But does that mean that the way we find the mass of the exciton would essentially be that inverse sum?
Yeah, that's a good point, is that maybe that's how you would use that to calculate the mass of the exciton. I have a feeling that this sort of term preceded this relationship, but yeah, that could definitely be a way to do that. Yeah.
So we think of these holes as having mass. How do we get to how do we understand the mass of a hole, which is in theory just a lack of.
I mean, how do you understand the mass of an electron if it's a wave, right? Isn't that hard enough? So now the opposite of a wave, what is the mass of the opposite of a wave? Right? That's tough, right? And so it's the particle duality of electrons, right? And so this absence of energy, or just the opposite kind of energy that the electron leaves when it moves, has a mass. So maybe, right? I mean, that is kind of a. I mean, maybe you can think about it in terms of this too, right? And so if there is some energy associated with that electron and some energy associated with that hole, then it should be related to mass in some way, right? Even though it is actually a wave, okay? So somebody asked me about practical applications last time. So this was a project that I did, and so here we were looking at lymphocytes, and specifically, so lymphocytes have all these cell surface markers, and that's what this is supposed to represent. And so the ones that the HIV virus specifically infects express CD3 and CD4. CD stands for cluster of differentiation. So there's like CD1 through CD200, and they all kind of are like a fingerprint for a cell. So if you have a cell that is CD3 positive, CD4 positive, CD56 positive, and CD81 negative, it'll have this kind of function, right? So we wanted to find the ones that were just positive for these two things, because then we could count how many lymphocytes you had and whether you needed to be started on HIV meds or not. And so we used quantum dots, and so yeah, we did that last time. And so blah, 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 blah. So then we had these different sizes of quantum dots, blue through red. And so here's some TEM images of these, blue through red. So the blue ones are around 10 nanometers. I'm sorry, the red ones are around 10 nanometers, the blue ones are around 3 nanometers, just like we saw in that chart earlier. Okay, so here's a question then. So these are the quantum dots that I was using. And this is the fluorescence spectra. Do you get what we're doing here? The red curve here is the wavelengths that I'm using to excite, and the red curve is where they emit fluorescence, okay? Excitation curves, emission curves, right? Red, green, and blue. So one thing you might say is, this doesn't look like this, right? This here we said that would only be one state, one energy. And as I look through here, there's a range of energies for each of these different colors. Why do you think that is?
Is it absorption and re-emission?
No, more practical.
Is that due to temperature?
No, because they're all at the same temperature.
Use quantum dots to get a heterogeneous nature.
There you go, right? Because when you look at when you go back and look at the TEM, so see how this one's like, maybe you can't see it, but this one's like more ovular. This one is, or this one's more cylindrical. This one's more ovular. This one's more spherical. So if you could actually make a truly monodispersed population, then you would tighten that that band gap up even more, right? But the yeah.
Because they're not uniform in shape.
That's right, or size, right? So maybe you have some like this and some like this and some that are like that, right? And so if you could isolate a truly monodispersed population, then you would start to hit
And
closer.
then this one's measuring the cluster of the majority,
What?
like all of them.
Yeah, exactly. So this excitation and emission curve was done on all of these. Yeah, yeah.
But side question, how could we select for monodispersed mixture?
That's tough. There's a technique called field flow fractionation. There's a by far the better bet is to synthesize them cleanly and rather than try to purify. Because to try to purify particles, you can do differential centrifugation. On shapes like this, it's really tough. Yeah, it's purely a synthesis thing, yeah.
Is there a benefit to communicating a quantum dot to an antibody rather than just a fluorophore?
Yes, there is, and the advantage here was that, so when we looked, so here I needed a two-color system, right? I wanted to look at CD3 and CD4. So if I wanted to use a molecular fluorophore, this is the optics I'd have to use. A polychromatic light source, pick my green, come down, excite my sample in green, and then filter again for the green emission. Red, filter for red excitation, filter for red emission, right? That's what this is for a molecular fluorophore, right? Excitation curve, emission curve. What I can do with quantum dots is I can excite them all at the same channel, right? So now I can just use a single filter cube. So if we were trying to build this miniaturized device, I cut my light sources in half and my optics in half by being able to use this kind of system, right? Because here I have one UV excitation source, gets me all of these colors, right? You guys know what the difference between this is? Excitation peak and emission peak? It's called the Stokes shift, if you ever heard of that. So generally you want a large Stokes shift. So then what we could do is red plus green equals yellow.
Is there a limit to how many different colors you can do with the same device?
3 or 4 is generally pretty easy, depending on for this kind of miniaturized system. So red and green equals yellow, and then so this was with 2 different molecular fluorophores, and this was with quantum dots. So the yellow is not quite as yellow, but we could still definitely deconvolute that out. And then we could just go on and do counting, literally, like with image processing, and process that out, overlay, and then start to count. Okay, so now let's on to another way of thinking about extended solids. Come on. Okay. So today we're going to talk some more about the tight binding, well, we are going to talk about the tight binding model, which is a way of thinking about extended solids from more of an analytical wave function perspective. Okay, so what we had been doing with these extended solids and semiconductors is we haven't yet really done approximation or evaluation of the wave functions, right? We've kind of just said, there's one big wave function, how many states are there in it, right? Or how many wave functions do I have? That's what the density of states was doing, is how many wave functions do I have? And now we're going to start to analytically understand the contributions of these unique wave functions in the component atoms, okay? A little bit better. So we're going to use what's known as Bloch's theorem. And this is saying that in addition, so this is the energy well from all the individual atoms that are in our system, right? So here's each of our, say this is linear hydrogen, right? And there's a potential energy well at each system, right? What Bloch's theorem says and what the tight binding model says is that not only are there these individual atoms that are periodic, but there is a wave function for the entire extended solid that binds those together. Yes?
So that means that the wave would start up and hit the atom and then it would go down once there's a well. Sort of.
Yes. Where's my best one that shows it? I like this one, where it's showing that we have the gray ones here are the individual atoms, and then the dashed black one is this periodic function across the entire extended solid. So you believe that that happens? It's kind of, the Bloch's theorem, it's a theorem, but data shows that not only do you have these individual components, but you also have this periodic function across the entire piece of semiconductor. Yeah?
Wouldn't that also depend on orientation? Positive, negative, negative, positive, or negative, negative, positive, positive?
Yeah, I mean orientation in terms of if the dimensions are different,
Yeah.
right? If you had a perfectly spherical or cubic piece of material, then probably not. But definitely yes. So what we're going to talk about, the example we're going to use is going to be linear hydrogen, our friend linear hydrogen again. So we're, of course, going to be looking at that axis, not that axis, right? Okay. Read the book on the, read this section. I think it's one of the best sections that we've had yet. So if we are imagining this kind of system, which we've looked at before, where we have H, and here we're starting numbering at 0 as opposed to 1. So hydrogen 0 through N, right? And remember when we had a 2-component system, 1s, with a sigma and a sigma star, right? We could show that the wave function of this was a weighting function of 1 times the wave function of 1, weighting function of 2, wave function of 2. Right? No big whoop. So similarly, if we had an H3, and so on and so forth. Okay? This is a key assumption. In the case where all atomic orbitals equally contribute to the linear combination of atomic orbitals, Cn is 1, this is a typo, C should be 1 over the square root of n. It approximately equals that for a 1D chain of H. Okay, so how do we get that? If we have, okay, and if we were to normalize this, we would do this, right? So here we would do right? We're just squaring it, okay? In this kind of situation, we can clearly assume that C1 equals C2. Okay? So then we get C squared phi 1 squared plus 2 that. Right? We know that this equals what? 1, yes, and this equals 1, right? So now we can simplify this to, let's skip a step.
Sigma 1 and sigma 2 are orthogonal, so would that term go to 0 then?
It doesn't, and this is an assumption. In this situation, we're going to call it's what's known as the overlap integral. We're going to assume that it's very small. We're going to basically assume that it goes to 0. Yeah. Yep. And so this becomes 1 plus the integral plus 1. Okay, so if you rearrange this and let's just call this S, the overlap integral. So then we can solve for and just like you said, we're going to assume that this basically goes to 0. So in this situation, our C is 1 over the square root of 2. And hopefully you can appreciate then, as this goes to H3, H4, H5, Hn, hold on, we're going to have phi 1 squared, phi 2 squared, phi 3 squared, phi 4 squared, phi n squared. So we're going to have up through n. So that's why our C to the n term is 1 over the square root of n. Yes?
As you have more hydrogens, don't you get more overlap integrals and more combinations of these overlaps? So is there an additive effect?
There is, yeah, and it's a key disclaimer, and that's the graduate level course, is to consider those overlaps. Yeah, but on balance, we're not losing a lot here. This is a pretty safe assumption. Yeah.
Such a good question. Notice
Yep.
the original wave function and the integral. We have HS.
Yeah, that should be. God, R's are 2s and S's are 2s. Everything's 2 except for 2. Yeah. Yes.
So I noticed that we started with 0, like you mentioned
Yep.
here. And then we have n. So is this really n minus 1?
No. Why would it be?
Because if we have...
Oh, yeah, because of the different nomenclature here. Yeah, technically. At some point, n's, I mean, in these extended solids,
So number 1 isn't going to be...
minus 1 is going to be, yeah. Yeah, I mean, here, if I would match what was there, this would be C0, that 0. Yeah.
So how is this different for something that's not just a one-dimensional solid?
We're going to hopefully get there. Yeah. Yeah. I mean, what would you do? You would integrate this in 3 dimensions, right? That's what you would do, rather than just in this 1 dimension.
So it would be a triple integral?
Yeah.
That doesn't sound like fun.
Okay. So at if we had then thinking back to this kind of system. Okay, where this is our E0, this is then H2, H3, H4, H5, so on and so forth, right? At the bottom of the 1s band would be the linear combination of atomic orbitals representing our most bonding combination. Bottom down here, right? Where all of our bonding orbitals, our 1s orbitals, overlap. Okay, so this is showing it through two different representations. So this would be kind of the individual hydrogen element or hydrogen atoms, and then the solid one is their overlap. Okay? Similar, this is if they're all bonding. They're all going to look like that. As opposed to what we would have at the very top, right? At the top, we would have this alternating bonding and anti-bonding, right? This is an all anti-bonding spatial representation, which would be up here, which is not going to be occupied, right? Yeah.
So for example, like when you increase the hydrogens, does that mean that you also increase the number of potential wells?
Absolutely. Yeah, right? Because you know that's one of our cardinal rules is that the number of atomic orbitals has to equal the number of molecular orbitals. And so as you add in more molecular orbitals, more atomic orbitals, you add in more molecular orbitals. That's what this is. That's what this is showing, right? And that's what our density of states was looking at. Yeah, partially. Okay. So what about in the middle here, right? What about our situations where we have kind of occupied orbitals? Here's where we use this mathematical expression, this block function, as a wave function to describe this periodic structure in the middle, right? Because it's kind of easy to think as, well, once they're filled, they're filled. But there is a wave function within the middle of these energy levels, okay? So it's, and yes, and so these are periodically repeating occupied orbitals. Yeah.
So if I'm understanding this correctly, an atomic well would be in the density, or I mean, where the electrons are least likely to be?
No, this is the lowest energy.
That's where they're
Most likely to be. Yeah. Yep. So does this show it? This is kind of a weird way of looking at it. This is the most likely location to have an element. And so if this was instead of hydrogen, if this was like linear sodium, you would think of 1s2 being here, 2s2, 2p6, 3s1 up here. Finally, where you get to your valence electrons would be at the top-ish of this well, and then these 3s is where they would do stuff together. Yeah. Okay? So what this function describes then is a notion of periodicity on top of our linear combination of atomic orbitals. Okay? So here, this wave function is wave function z, so in the direction parallel to the bond axis, which kind of goes back to your question, Mohammed. Yeah?
The I, K, Z term just looks like a regular sine or
Cosine.
cosine function.
Yeah.
Shouldn't, if you have like a lot of those in the middle, shouldn't there like be some sort of interference and interaction?
Yes, yes, yes. That's exactly where we're going. And so, and how can we use this to look at this interference and overlap? Yes. And that's what this was showing, right? That's what this is showing, is where here, this is that cosine function from the e to the I pi term, and these are the individual atomic orbitals, and how does this influence these, right? So here, this cosine function is amplifying this individual atomic orbital, And here it's minimizing that individual atomic orbital, right? So this dashed line here is from this term, right? And then the resulting output is this. It's not showing the individual atomic orbitals. Yeah.
Shouldn't there be like more peaks and troughs in the?
It depends what K is.
Well, like,
Right?
You have the for each of those peaks. Aren't there a lot of interactions between the subsequent atoms next to it? So shouldn't there be like more?
The most interaction is with the adjacent hydrogens.
It tapers off like a 1 over square root of n relationship, though, right? So shouldn't you still have like more? Like when it's going down, shouldn't it not just go down directly? Shouldn't there be like some sort of school? Yeah.
You mean where?
Like when it's going from like, yeah. Like shouldn't there be like more school there?
More like it shouldn't be as steep?
Yeah.
It depends what the K is, right? So what if K was 0 here? What if K is 0? That means there's no periodic function, right? So let's solve that equation. So if K is 0 here, we have e to the 0, C0, phi 0, plus e to the 0, C1, phi 1, plus e to the 0, C2, phi 2. Okay? So this is 1 plus 1 plus 1 equals 1 over square root of n, phi 0, phi 1, phi 2, dot, 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 dot. That's what this, our lowest orbital is. There's no periodic function there. Okay? What if K was pi? I had to go back and relearn this. I forgot about my unit circle and this relationship. You guys remember this? Read up on it. I'll give you the cheat sheet version, but they actually, there's a study on Wikipedia, there's a study where they put, I don't know, 20 mathematicians into, like really respected mathematicians into functional MRI and showed them different theorems. And by far, their brain lit up the most with Euler's identity. So it's a very beloved identity. What you need to know here is that you can use your unit circle to and the cosine identity. So let's do an example where K is pi over 2. Or not pi over 2, where K is pi. And actually, let's call it pi over a, because we'll show an example here. A is just going to be our distance between these two, okay? Which we can say is 1. Okay, so then we have e to the 0, C0, phi 0, plus e to the I pi C1, 0, 1, plus e to the I 2 pi C2, phi 2, plus e to the I 3 pi C3, phi 3. Okay. E to the I pi has to equal what? Negative 1, right? E to the I 1 plus 1 equals 0, okay? So this one's easy. And we know that e to the 0 is 1, right? So 1 0. 2 pi is 2 pi is now 1.
Was it should that be negative one?
Blah, you just said that. Now we're back to 1. -1. Right? What I'm doing here is looking just on my unit circle and the cosine function on my unit circle. So at pi, my cosine value is -1. 2 pi, my cosine value is 1. Okay? So then this simplifies to what's this term? The same, right? 1 over square root of n. Okay? That's what this is showing. Okay? So this is an all anti-bonding situation. So this is at the very top. Yes?
What does K represent?
It's the wave function of the periodic lattice. A wave function that is completely decoupled from the individual atoms, but that represents the wave function of the entire extended solid. So it's this summation then is the interaction between those two.
Is it something to be specific for a certain material or something like that? Or is this, would you have all
of these frequent
orbital you're looking at?
You would have, yes, you would have all of these frequencies at the same time, but to differing degrees. Yes. Yeah.
So is that why the C term is there?
Is that why the C term
Is there to like,
C is not specific to your material. C is a weighting function that is essentially helping you assume that each of the atoms, at least in terms of this contribution, are most strongly interacting with their nearest neighbors. Yeah. Yes?
Earlier you called K the wave number.
Did I say, yeah, wave function is a more accurate description. Yeah, how did I?
This is wave vector.
Okay. So so the overall, this is your overall wave function for the material, okay? That involves both the periodic function and the K wave vector. Okay, where our vectors here are all going to be in the z direction. So you could have other wave vectors in other dimensions.
so the K just depends on the atomic size, isn't it? Because it's dependent on the A, which is the distance between the center.
Yeah, that's definitely going, yeah, exact.
That's why it's a vector.
Yes, I think you can think about it that way.
Is it the Z that gives us the vector direction?
Z totally gives you the vector direction.
So K is more the scale of one. We're calling it a vector because we're applying it to Z. Right?
Yeah. If you search for block function online, the number one thing that comes up is this as R, right? Most of the time this shows as R for any given point, and then this drops away and it's the three-dimensional linear combination.
K would be a function of all bases. Right?
Yes. So here we're just looking in the Z direction. Yeah. Okay. So I'll let you prove it to yourself that if we have this, what would this be? Test yourself really quick. This is what it looks like spatially, but what would the wave function look like? You even have your unit circle. Because this pi over 2 term, every other one is going to be 0. right? 0 is 1, pi over 2 is 0, pi is negative 1.
And why wouldn't we see our third circle as shaded? We just seem to have alternating 1 and 0.
Well, there's a
Because when you have 3 over pi, 3 pi over 2, you also have a 0.
Right, but why don't we have any negative 1 here?
Pi over 2, pi and 3 pi over 2.
at the pi, you mean?
Yeah, 2 pi should be
Yeah.
negative 1.
So it should be like a shaded thing?
Yeah, because at 2 pi over 2 we have negative 1.
So it's non-bonding, but it alternates also between like a shaded and non-shaded.
It goes 1, 0, negative 1, 0, 1.
Yeah. That makes
That sure is what it should be. But why, is that where the I comes into play?
That's what I'm wondering about the I. 'Cause shouldn't every other one be I? It should be the square root. So the half would represent, right?
The half,
Half power would be
Yes.
the root. So it should be I in each of those dark spots, right?
Dark spots are 0s, aren't they?
dark spots are zeros. Yeah, that's a non-bonding situation. Yeah, okay, that's on my to-do list. Okay, could you then start to represent, regardless, what would this be? What is K on these situations? Yep. Right? Does everybody get how they're seeing that? So the top one is definitely pi over 4 because the period to get between here and here is pi divided by 4a's, right? The better way to think of this is pi over 4 times a. Okay, so here, where this is 1a, and this one you've got 1, 2, 3, 4, 5, 6.
Because
6a.
originally we approximated A as well.
Yep. Yep. Okay, so then people also think about this in terms of what's known as a band diagram, where here you can plot the total energy that's more stable and less stable relative to the original energy as a function of these different K values. Okay, so here at the very bottom is our all bonding, top is our all anti-bonding, and here are these non-bonding situations. Okay? This is then what's known as the band width of a specific material. And then you can back this out, we're not going to derive it, and show this relationship between the bond energy between neighboring 1s orbitals, the 1s atomic orbital energy, which is negative 13, K 0.67, whatever, eV, and then the cosine is from the block function. Okay? And so here you can look at how does this change, how does this bandwidth change as a function of different bond widths. Beta is the bond energy. Okay? Okay, so this is still not clear in my mind why that's the only thing that's still not clear. I'll look at that and get back to you on Friday. Read this section. If you read any section, read this 3.3. It's really good. Okay?